Hello, everyone. Thank you for attending this session about roaming in Cisco Catalyst Wireless architecture. It's a real pleasure to be here. Thank you, Matt, for inviting me for this amazing event. My name is Hafida Barhoun. I'm a technical solution architect at Cisco. I'm also part of the Cisco Live NOC team in the wireless deployment team. Unfortunately, this year I couldn't attend because I'm freshly mom of 2 kids. The first one looks like his mom, whereas the second one is a copy of his daddy. So we have 20 minutes together to talk about roaming, the different types and techniques of roaming, and some best practices. If you have any question, please, let's keep it at the end of this session. And if we don't have time, let's have just a small chat at the coffee break. So roaming, when we talk about roaming, what does that mean? Different than the definition of roaming in mobile networks, roaming in Wi-Fi occurs when a user and his device are moving from the coverage area, or what we call a BSA, basic service area, of one access point to which it's originally connected to the coverage area of a second access point, okay? More than just this movement from one AP to the other, it's the ability to maintain user association seamlessly, securely, and with as low as possible of latency, right? It has to be transparent for the end user. So how do we do that? First of all, by making sure that my user can see and enjoy the next AP way before losing its signal, right? So to do that, the first thing that we have to do is to overlap a bit those coverage area to be sure that my user can have time to roam. So we're gonna see some roaming techniques about how we can achieve the fastest roaming possible after ensuring that by design, my user can see the next AP and roam properly. And the idea here is not to explain all the algorithm of each technique, so otherwise we're gonna still be sitting here together tonight, but more to understand how we achieve the fastest roaming possible. So when we configure our enterprise network Wi-Fi, we configure our SSID to be secure with secure authentication. And to do that, we have 2 main methods, WPA2 PSK using a pre-shared key, or WPA2 Enterprise, or WPA2 IP, using a user credential and an authentication server to do that with 802.1x. We have WPA3 as well, but we won't have time to talk about it today, okay? So when we do that, we configure when we use pre-shared key, we configure a static password on our end device and on the 9800 controller. This password is never exchanged directly between the end device and the controller. Both WPA2 pre-shared key and WPA2 Enterprise use the same rules to derive what we call the encryption keys. So we will have the first key that is called the PMK, the pairwise master key. And then we'll have other keys, one that will be derived from the PMK, the PTK for unicast traffic, and the GTK for broadcast multicast traffic. This process of deriving keys is called the 4-way handshake because we have 4 messages. With 802.1x, the process is quite similar, except that instead of generating the PMK, the first derived key, from a static password, we use a dynamically generated password at the end of the IP authentication. And that happens before I will check it out. So that's a high level of messages in the IP call flow. Right? So at the end of this authentication, 802.1x authentication, that happens after the reassociation request, but before the 4-way handshake. In the IP success message, we have an attribute ID that will allow us to derive this PMK, okay? So what about roaming? Why do we talk about all of this? Because going through the 4-way handshake when we talk about the pre-shared key is not that a big deal. That can take some time, but that won't break the service. Okay, we can do better, obviously, and we're gonna see how, but that's not necessarily an issue. The issue when we talk about roaming and authentication is when we come to 802.1x authentication, because that process is taking too long not to break the service. Because as we saw before, we have more messages exchanged, and the number of messages and the messages themselves depends on the method that we use for HIP authentication. It can be HIP, TLS, FAST, PIP, etc. So the issue is when we have to do the full authentication for 802.1x, and we're going to see how we can avoid that. So my recommendation here is that we have to avoid as much as we can the 802.1x authentication. And how we do that? We do that with different roaming techniques. So first of all, quickly, we're going to see an overview of the different techniques. We had OKC, Opportunity Key Caching, introduced by Microsoft, that allow us to replay only the four-way handshake, but not the 802.1x authentication. It has been widely deployed. We had as well CCKM, Cisco Centralized Key Management, that allowed us to bypass the four-way handshake and the 802.1x authentication. So it was a bit better. We had better performance, but it was proprietary. And later, we finally had a standard 802.11 or fast transition that achieved the best performances by avoiding to replay the four-way handshake, the 802.1x authentication, and even start communicating with the target IP while still transmitting data with the previous one. Okay, this is the recommended method today, and the end devices majoritarily support it. So now that we saw the different roaming techniques, we're going to see the different types of roaming in Cisco Catalyst architecture, wireless architecture. So we have two types of roaming. The first one is the intra-controller roaming, or the roaming that occurs between two APs managed by the same 9800 controller. Or we have the inter-controller roaming, and sorry for my English if it's a bit pronouncing the same. So inter-controller roaming happens when we roam from one AP managed from one 9800 controller to another AP managed by a different 9800 controller. In this presentation, we won't talk about roaming that happens between two APs managed by two different controllers from two Cisco generation, for example, C9800 controller and the 5520. So intra-controller roaming, first type of roaming. Here, my user, let's call her Mia, is moving from AP1 to AP2. As she moves, she will ask to reassociate to AP2. This request will be sent to the 9800 controller, which will simply update its database. Simple, fast. That's the best roaming type that we have, and this is the one that we recommend. Second type of roaming is the inter-controller roaming. In this type of roaming, we have two different scenarios. The first one is the layer 2 inter-controller roaming, and we have the layer 3 inter-controller roaming. In the first type of scenario, Mia is moving from AP2 to AP3, managed by another 9800 controller. Both controllers share a common subnet and use the same VLAN ID. They are also part of the same mobility group. We call a mobility group a group of controllers that are identified by the same group name, and where fast roaming using 802.11 or, for example, can be achieved by dynamically sharing data like the databases, security keys, and more. So in that example, when Mia will move from AP2 to AP3, she will ask to reassociate to AP3. WLC2 will send a mobility message to every controller inside the mobility group saying, hey, do you know Mia? Controller will answer, and in that case, WLC1 will answer saying, hey, I know Mia. I have her in my database with this context. I'll give it to you now. So Mia's context will be forwarded to WLC2, and WLC2 will update its own database with Mia's new AP, here AP3. Second scenario with inter-controller roaming, the layer 3 inter-controller roaming. In this scenario, Mia moves from AP4 to AP5. She walks a lot. It's a really big campus. And both controllers are still inside the same mobility group, but this time, VLAN IDs are different. They use different VLAN IDs. And this scenario, we differentiate point of attachment in the network than point of presence in the network by creating an anchor relationship between both controllers. By doing that, when Milia will ask to reassociate to AP5, her context will be copied to the foreign controller, WLC3, and at the same time, she will be tagged as anchor in WLC2 and foreign in WLC3. A symmetrical data path will be established between the two so that Milia's traffic always flow back to her anchor controller. In that way, seamless roaming can be achieved because the original IP address doesn't change because she's still anchored to WLC2, and fast roaming can still be achieved. We don't need to re-authenticate again. Obviously, that can add some latency, and this requires more compute and more loads on the 9800 controller. So we recommend to avoid as much as you can this type of inter-controller roaming by keeping all the APs inside the same roaming path, managed by a unique controller and do intra-controller roaming. And if that's not possible for whatever reason, try to do layer 2 inter-controller roaming. So what's different between layer 2 and layer 3 inter-controller roaming? How do we differentiate them? By using the VLAN ID. Previously, with ROS, we were using the subnet. Today, with the 9800, we only base the decision on the VLAN ID. So if it's the same VLAN ID on both controllers, then it's layer 2 intercontroller roaming. If it's different VLAN ID, then it's layer 3 intercontroller roaming. Be careful not to play by putting the same VLAN ID but different subnet, because otherwise you will break the roaming. When we configure seamless roaming in Flex Connect architecture, we have to create what we call the Flex site tag. A Flex site tag is a group of APs that, where fast roaming can be achieved by caching the security keys of the end devices inside all the APs of a Flex site tag. For example, in a remote site, I will have 4 APs. I'll create a Flex site tag with those 4 APs, and the security key, the PMK to be more precise, will be shared among those 4 APs, so that when my user will ask to reassociate to another AP, she won't have to re-authenticate. Now that we saw the different types of roaming and techniques, in this last section, we're going to see how we can influence roaming to optimize it. Because as you might know, roaming is an endpoint decision. It's always taken by the endpoint. The decision is always taken by the endpoint. And you have 4 main criteria. Either it's the threshold, the RSSI is going below a defined threshold, or it can be because of the SNR, because it's bad. It can be because we exceed the max retry count, or it can be anything in a proprietary algorithm, or it can be just because my devices is now want to listen for the infrastructure guidance. Roaming algorithm may vary from one vendor to another. Here you have an example of iPhone and Samsung, for example, where iPhone decide to roam when the RSSI goes below minus 70 dBm, whereas Samsung do it with minus 75 dBm. So it's the endpoint decision, but that doesn't mean that we can't influence it. So how can we do that? First of all, by playing with the coverage, and to be more precise with the data rate. Because putting higher data rate will encourage the endpoint looking for other APs, and we're going to see how. And then, by playing with 2 standards, that allows us, first of all, to build a list of surrounding APs, and then tells us to which AP we should roam to. So the data rate. When we configure our Wi-Fi, we have to declare which data rate are mandatory, meaning which data rate are mandatory to be able to connect to the AP. That's the lowest mandatory data rate. And then we have the AP, the data rate that we support. That means the data rate that we can support, for example, when my user is connected to the AP, but is moving away, for example. So putting higher data rate will stimulate the end device looking for APs more often. But be careful when you play with data rates, because the higher the data rate is, The more the signal has to be cleaner, the signal has to be better, meaning being potentially closer to the AP. So the higher the data rate, the smaller is the cell, and the better the signal has to be. Okay? So in an existing deployment, playing with data rate might not be the best idea because otherwise you can create coverage hole, and that's obviously not what we want to do for roaming. But if you have enough density, that might work, but it's worth thinking and studying a bit. On the other hand, data rate can exclude some modulation. Data rate ties in modulation, that ties in Wi-Fi standard, right? So if we exclude data rate, then we can exclude some Wi-Fi devices. For example, in 2.4 gigahertz, if you exclude 1, 2, 5, and 11 megabits per second, then you exclude 11B devices, and IoT team might not be super happy. 802.11k. That's a standard that allows the end device to build a list of surrounding APs and try to optimize the scanning and roaming behavior. So without 11k, what happens is that what the device has to roam, he will have to do a full scan of all the channels. For example, let's imagine it's connected to 5 gigahertz channel. Then it will have to scan every channel one by one, so 36, 40, 44, 48, 52, and so on. With 11k, what we do is that we say, hey, there is a short list of optimal channel. You should have a look. And then with 11v, what we do is that we suggest to which AP the end device should roam to. We have multiple options to do that. The first one is when the end device asks for help, saying, hey, AP, do you know, what do you recommend? Which AP do you recommend to roam to? Another option is the infrastructure that proactively advises, saying, hey, you know, your SSI, your data rate really sucks. You should roam to AP3. Another option is from the AP that wants to roam and connects to another AP, and then the AP gently answers back saying, hey, I'm sorry, I'm too loaded. You should roam to AP3. Then, when we talk about roaming, one thing that is super important is to understand how people walk and how they roam from one AP to another. So this little example to illustrate this. So in red, you have the APs. In blue, you have the user path. And in the middle with the cross, you have the lifts. Here, the question is, what is the best AP placement to optimize roaming? Raise your hand if you think it's example 1. Raise your hand if you think it's example 2. Raise your hand if you have no clue. Okay, great. So let's see how it goes. In example 1, at point A, my user is connected to AP1. As it moves down to point B, it will acquire AP2 in its neighbor list, right? But it won't have the ability to scan AP3 because of the RF shadow caused by the lifts, okay? When it will arrive at point C, he will have to roam, but the only APs it will have in its labor list will be AP2. So he will go on panic mode, and he will try to rescan for AP3. Here we can have a potential roaming problem. If we compare to example 2, at point A, my client is connected to AP1. When he goes down to point B, he has neighbor AP2 in its neighbor list. When he arrived at point C, he has to roam, and he will have AP2 in its neighbor list. So he will be able to roam to AP2. And then when he will carry on moving, then he will be able to scan, have time to scan AP3, and then connects to it. So here, team example 2, you won. Congratulations. That's a really great example on how and why we should know how our users are moving and what are the constraints of our building. Another false good idea about Wi-Fi is to think that putting AP at the maximum power level will make a good design because, you know, with one AP I can cover more. So why you should not do that today, So design your wireless for coverage only. With this small example, so my AP here can yell very loud at 100 milliwatt, for example, 2.4 gigahertz. And my devices, my end device, will be able to hear properly, even if they're far away. That's the goal, right? But what about the end devices? They can yell as loud as the AP, right? You can divide by 4, around by 4 the power level. So what will happen? Let's imagine that my end device is at the border of the cell because it's as sticky as an ex-girlfriend or boyfriend, or because the design doesn't propose something better. He will hear the probes coming from the APs, answer back again and again, but the answer will never get back to the AP. That's a good way of degrading Wi-Fi performances, isn't it? And more than that, you can be pretty sure that every RSSI heard at the border of the cell will be crappy. So what's the solution for that? A solution that makes Wi-Fi vendor infrastructure like Cisco really happy is to densify your design by buying more access points, right? So our recommendation is to have enough AP density and to let a Cisco algorithm, RRM, Radio Resource Management Algorithm, handle the power attribution automatically and let it adjust dynamically in case, for example, if we lose an AP. One last advice is to be always careful with what you activate. Okay? Be careful with the feature, even if they have a really nice, fancy marketing name. Be sure to know what you're playing with. Two quick examples. With optimized roaming, for example, here what the feature does is that it proactively disconnects clients if the signal heard is below a defined threshold. And more than that, if the end device comes again to the network without having 6 more dB, then it's not accepted anymore in the network. That's really aggressive. That works pretty well with sticky client, but that can be the opposite of what we want to do with roaming. Another feature that is super great that is called Eric's SOP, which will decide when to demodulate a frame based on a defined threshold. Here, what it does, to summarize, is that we tell the AP when to ignore clients. And this feature is super useful, for example, in very high density design, because we can create smaller cells and achieve high level of tuning, but be sure to master your environment to do that. This is not a feature that you want to activate one day because it looks cool. So to summarize, I put some do and don'ts about roaming, and I will give you one last advice, and I swear that's really the last one. And it will be to always design with a proper site survey before but after the deployment, and that links to Mac and Matt's presentation today, because you really want to validate your requirements and be sure that your roaming is going as you would like to, and that you have the level of performances that you want. Okay, this is where our friend from ECAHO comes into play, and there is a saying from one of my colleagues, Federico Ziliotto, that I really like, that says, if you think that a good site survey can be expensive, wait to see a bad one. So that concludes my presentation. Thank you again for attending. I hope you enjoyed it.